Okay, we're going to look today at finding roots of complex numbers, which is an interesting little concept. So, for example, we've got complex number to the power of 4 equals 2 plus 2i root 3. We're going to try and find what z is. We're basically going to find the fourth root of this complex number here. So we start off by looking at the complex number and getting it into the different form. I need to look at the modulus of it and the argument of it. So I'll look at 2 plus 2i root 3. And it's going to be root of 4 plus 12 root 16, which is 4, and the argument is 2 root 3 over 2 root 3, which is pi over 3. If it's got minuses in, I would always recommend doing a sketch so you know which quadrant it's in, like that. So I know that we're trying to find the fourth root of 4e to the I pi over 3. And what we've seen before is the fourth root of 4 and then times by the fourth root of this, which is e to the I pi over 12. There's a but, and this is now where we get our other solutions. In this case here, because we're going to get 4 solutions, I need to end up with turning this power into other powers that have got the same argument as this, but then when they divide by 4 it gives me 4 different answers. So what I do with this, I take this pi over 3 that was there and add on a multiple of 2 pi, and then I can divide it by 4. So it's the divide by 4 because I'm finding the fourth root. And then basically sticking nice positive or negative whole number powers of k. So k equals 0. I've got my first answer for z equals fourth root of 4 is, well, the root of 4 is 2, so it's root 2 e to the I pi over 12. Our basic answer that we got there. K equals 1, z equals root 2, and I'm adding on 2 pi over 4, which is pi over 2, 90 degrees basically. What it's going to be, when I'm sketching it, everything will rotate 90 degrees around. So adding on pi over 2, or 6 pi over 12, gives me 7i pi over 12. If I chose k equals 2, I'd be going beyond. There's k equals 0, there's k equals 1, k equals 2 will be going that way, so I need to stick in k equals minus 1 and end up with 1/12 minus 6/12, which is e to the minus 5i pi over 12, which is that way, and k equals minus 2, z equals root 2, take another 6 off that, e to the minus 11i pi over 12, which is that one there. What we'll find is these should be equally spaced around a circle of radius root 2. And in this case, because it's the fourth root, I've got 4 equally spaced answers, so there'll be 90 degrees, pi over 2 radians between them. So the twist is, whatever that argument is there for our complex number we're trying to find the root of, we need to add on multiples of 2 pi onto it. And then when I use the De Maas theorem to times the powers together, like this, we end up with the fraction that I've got there of pi plus a fraction of 2 pi, multiples of 2 pi. And choose values there, so that's k equals 0, that's k equals 1, k equals 2 would have been out of our range, so k equals minus 1 going that way, and k equals minus 2 there. That's our 4 solutions for that. We have found all the fourth roots of that complex number. Second example, solve z cubed equals, so we're going to find the cube root. So z cubed plus 8i equals 0, rewrite it as z cubed equals. And as before, turn it into modulus and argument form, e to the minus I pi, not minus, pi radians like that. So z then is the cube root of that, cube root of 8, 2, pi over 3, plus 2k pi over 3. And as before, I'm going to get 3 answers now. K equals 0, k equals 1, and something else, probably. So k equals 0 gives me z equals 2 e to the I pi over 3. K equals 1, I'm adding on 2 pi onto that one, so z equals 2 e to the I pi, and k equals minus 1 gives me the other one, so one of them minus 2 of them, 2e to the minus I pi over 3. And what we should get, equally spaced, pi over 3 pi minus pi over 3. So k equals 0, k equals 1, k equals minus 1. Circle, radius 2. So all I've done, I've taken the cube root of the 2, sorry, the cube root of the rate to get 2, the cube root of e to the I pi becomes e to the I pi over 3, but I've then added on multiples of 2 pi onto it, and because I'm finding the cube root, I'm dividing by 3. And then sticking k equals 0 in gives me just the pi over 3 one there, and then I'm rotating round because these are now equally spaced, so each one of those is adding on or taking off 2/3 of a circle, 2 pi over 3. We can also, deal with fractional powers, so not just 1/3, 1/4, but we can solve equations like this. So z to the power 3/4 equals this thing here, so z will equal whatever root 6 plus I root 2 is to the power 4/3. And as before, I need to take this complex number here and deal with its modulus in argument form. So the mod of it is going to be root of 6 plus 2, root 8, or 2 root 2. E to the root 2 over 6 is root of a third, 1 over root 3. So it's, because it's nice and positive, I pi over 6 to the 4/3. So z will equal 2 root 2. Because I've got fractional powers, I'm just going to rewrite that as 2 to the 3 over 2. And I know that's going to be raised to the power 4/3. I can simplify that, times e to the I, pi over 6 times 4/3, 4 pi over 18, or 2 pi over 9, and then plus 2k pi times 4/3, which is going to be 8k pi over 3. So in that case there, thank you, I'm going to have a variety of answers, not as easy because it's fractional powers. See what I get. K equals 0 gives me whatever the mod is of z, 4 over 2, 2 squared, 4, e to the 2I pi over 9, k equals 1, z equals 4, so I've got 2 9ths plus 8/3, and that might end up being out of my range. So k equals 1 probably gives me an answer that's outside of my range there, because I've got 8 over 3 is bigger than 2 pi. Yep, so that's out of range. k equals -1. Might just about get away with it. I've got 2/9, and then -24/9, and that's also out of my range. I've only therefore got the one answer for this fractional power here. So z equals 4e to the 2I pi over 9. And that's how we deal with powers of and even fractional powers of complex numbers.